Well, using those hybrid pi models, so I went over how to use it and the equations we use and so on. So if we had this amplifier here, if we had an amplifier, an NMOS transistor, where we have an input signal generator on the gate, and we've got an output on the drain. So we've got 2.5 volts up here at VDD and minus 2.5 volts here at VSS at 25K. V out is right here, V in is right here, R sig and V sig. We'd like, if that's what I want to analyze and find the small signal gain and things like that, we've actually got enough to calculate things. So the first step would be to find the hybrid pi model. So if we just draw it, we've got the current source, GM VGS, that VGS right there, got R naught, and a load. And we have a signal generator. I could connect all those together, I suppose. V sig, R sig, plus minus VGS, GM VGS, R naught, and RL. We need our drain in here, don't we? So let's see, we've got 15K. Let's there's RL. And we have the gate terminal, the drain terminal, and the source terminal. It's always helpful to draw those in. So what do we, we'd always want to find R in, R out, AV naught, AV, GV, W over L. We'd like to know what the voltage V out is, or I'd like to know what the voltage on between the source and the drain is. Well, that's kind of a silly thing to say. It should be the same as V out here. And maybe what value we need for this voltage source, VGG, right here. What value do we need for VGG? So those would all be good things to calculate. So first we can find GM. So let's see now. What would we have some other information? I'll give you that ID is equal to 250 microamps, and L is 1.5 microns. Ancient technology, and V overdrive is 1/4 of a volt. Okay. Now with that, first off, we can just see the RN is right here. It's what the signal generator sees, and that's an open circuit, so Rn is equal to infinity. R out is a little trickier. we need to know the value of our out is a little trickier. We need to know this value here of R naught. So we've got to find that. So we might as well first find GM. That's just 2 times the drain current undivided by V overdrive. We've got these 3 equations, and this is the one we've got 2ID, and we've got ID and V overdrive, so that's the one we should use. And if we put those numbers in, we've got 250 microamps times 2, so 500 microamps over the overdrive is 0.25, and that gets us a value of GM of 2 milliamps per volt. And then R naught, that's VA prime times L over ID prime. ID prime is right here. We could call that ID prime if we wanted, but it's just the saturation current. So we've got a value of VA prime is 20. Did I give that last time? Yeah, here it is, 20 volts per micron. So we've got 20 volts per micron times 1.5 microns. Those cancel, the microns cancel. Over this current, 250 microamps. And that gives us R naught is a value of 120K. Okay. So that puts us in a position to calculate R out, because R out is what the load sees. Just looking back that way. This is the load. R out is what the load sees. So we stand in place of R out, and we see, what do we see? Well, we see the resistance down here, R naught, and we see the resistance up here, RD. So we can calculate that. It's these two, R naught and RD, in parallel. So if we put those values in, we have 1 over 15,000 plus R naught is 120K. And we get a value for R naught, or R out, of 13K. And we've got enough room for AV naught. The open circuit voltage gain, that's without the load, so that equation is minus GM R naught parallel with RD. So how do we know that? We can write the equation. If we write the equation of V out is equal to minus GM R naught parallel with RD minus GM VGS. This would be this would give us the voltage here, V out on the drain. We have this current, GM VGS, in parallel through these two resistors when we're not considering the load, open circuit. And so that's the equation we're solving, and therefore we would get AV naught is V out over VGS, which is V out over Vn, and that's equal to that. So I'll just erase that so it doesn't confuse things. And if we put these values in, we've got minus GM was 2 milliamps per volt, 0.002, and we just found R naught parallel with RD, it's 13K ohms. So I'll multiply that out, and we get minus 27 volts per volt. AV is exactly the same thing, except that it includes the load resistance. So AV naught was the open circuit voltage gain. AV will be the voltage gain including the load, but not including the signal generator. And so if we put these values in, we got minus 0.002 times 270K parallel with 15K. And did I say what a load value was? Still only cost 25,000. Yeah, 25K. So parallel with 25K. And that's going to be less than 10 or less than 15K. In fact, it'll be minus 0.002 times 8730, giving us a gain of minus 17 volts per volt. Oh, I skipped a page there, didn't I? Minus 17 volts per volt. Now, if we'd like to know GV, well, GV will be the same as AV because this is an open circuit right here. We have infinite input resistance, and that makes it so that AV is equal to GV, or GV is equal to AV. And then a kind of not a large signal question, but what is W over L? What is W over L? Well, we've got the saturation equation. We could find it several different ways. This is how I think I would do it. 1/2 mu n Cox W over L times V over drive squared. Why would I use that? Well, we've got mu n Cox, we've got V over drive, we've got ID. So we've got all the things except W over L. So solving for W over L, it's 2 times the current divided by mu n Cox V over drive squared. Put our values in. We've got 2 times 250, so that's 500 microamps. And mu n Cox is 125.6 microamps per volt squared. And V over drive is 0.25. And don't forget to square that. And we might as well just cancel off the e to the minus 6's. And that equals 63. So we need W over L to be 63. Then what's the value of V out? Well, V out is equal to V dd minus ID RD, which would be 2.5 volts here. Right? We've got that 2.5 volts minus the voltage drop in that 15K RL. So minus the current, and the current we have is 250 microamps. 250 e to the minus 6 times RD, which is 15K. So we get 2.5 minus 3.75. Now, is that scary? Is that not good? Well, it's okay because we have the lowest value of minus 2.5. So we're going to have a negative value here, minus 1.25, but that's okay because we've got this VSS, which is even more negative. So we still have a positive VDS. So V out is negative 1.25. In fact, VDS would be V out minus VSS, or minus 1.25 minus 1 or 2.5. So we'd have a plus 1.25 for VDS. Finally, I would like to know what this value of VGG should be. What's the DC bias we need on the gate to make this transistor work? Well, VGG would be the same as it's the value on the gate, and the source is at 0. So this would also be VGS, and we know that V overdrive is equal to VGS minus VT. So then we have VGG, or VG. VGG should be V overdrive plus VS. Wait, that's not VGS, because VGS is, so that's not true. We plus VS, we're looking for this voltage to this node right here, gate to source. So plus VS plus 0.7. It's actually minus 2.5 is VS. So we've got 0.25 minus 2.5 plus 0.7. Add that up, we get minus 1.55 volts. So that solves the whole common source.